Hello good people, I'm going to talk about biology. Well, straight up, that is a lie, but bear with me. A word of warning, this course is not for the faint of heart. There are intellectual and physical pleasures to satisfy needs both exquisite and gross. Am I overselling it? Possibly. However, there is no escaping the fact that biology is the study of life and all the subjectively wonderful and disgusting things that come along with it. The word biology comes from two Greek words, bios, meaning life, and logos, meaning word or reason. This might be a good time to let you know that sciences come with their own vocabulary, influenced by Greek and Latin. It might be a good idea to keep a running glossary of the terms that you encounter. Biology is a beautiful and complex discipline. The beauty comes from the diversity of living organisms that have evolved on Earth. And although there is diversity, there are a lot of similarities that bind all life. Once we get to the cellular level, humans are not that much different from goats or even dung beetles. On a larger Earth scale, there is no escaping the fact that life is interconnected. Human existence is contingent on many other organisms, and the loss of any of them negatively impacts our own chances of long-term survival. It is hard to fully appreciate biology without some understanding of chemistry, which is a study of matter. Matter is all the physical material in the universe. Everything is made of matter. Our galaxy and all the stars within it, the Earth, a taco, and perhaps most importantly, this goat. Matter is composed of atoms. These are tiny particles that are often represented as spheres. Note that although this representation helps us talk about atoms, it is not the truth of the atoms. Their reality, and I use the term loosely here, is very strange. We will touch upon that strangeness later on, but for now, thinking of atoms as spheres will serve us well. Atoms are seen as the fundamental unit of matter. The story of atoms started as a thought experiment by ancient Greek philosophers, most notably one called Democritus. He suggested that if we were to take a lump of something, say coal or iron, and started dividing it into ever smaller halves, at some stage, we are going to reach a point when we can divide no more. He called this indivisible particle atomos, meaning uncuttable or indivisible. Today we know that atoms can be split, and that there is a whole world of subatomic particles starting with protons, neutrons, and electrons. We will get to those later on. For now, the working definition is, atom is the smallest particle that retains the properties of matter. Not all atoms are the same, and different atoms give rise to different chemical elements. We can still use spheres to represent them. For example, hydrogen is often represented as white, carbon as black, nitrogen as blue, oxygen as red, phosphorus as purple, and sulfur as a yellow sphere. These colors are not necessarily truly representative of these elements. All of the chemical elements are listed in the periodic table of elements. It is a bit intimidating. As of the recording of this video, in the year 2364, there are 118 known chemical elements. The first 94 are naturally occurring, while the rest are synthetic, meaning they were made in laboratories and are usually not very stable. Nobody expects you to memorize it. It is a tool that provides a lot of useful information. The periodic table comes with its own vocabulary. The table is organized in vertical columns known as groups, and horizontal rows that are referred to as periods. Elements that are in the same group have similar properties. Most versions of the periodic table will have a zigzag line that divides the table. This is known as the amphoteric line. Elements to the left are classified as metals, while elements to the right are classified as non-metals. Note that hydrogen is an exception. It is on the left, but it is a non-metal. Generally speaking, metals have a high density and melting points. They are malleable and conduct heat electricity really well. On the other hand, non-metals have low density and melting points, they are brittle and conduct heat electricity poorly. Many things in nature are on some sort of spectrum, and so on the non-metal side, there is a group of chemical elements that are known as metalloids. They are not quite metals, but have some of the properties of metals. As they are not that important to biology, we do not have to worry about them at this stage. Element groups have their own collective names. All metals in the first group are known as alkali metals. The second group is known as the alkaline earth metals, and then we have the middle of the table, which houses the transitional metals. This is followed by the boron family, then the carbon family, and then we have the pnictogens, followed by the chalcogens, followed by the halogens, and finally the noble gases in group 18. What about these two rows beneath the periodic table? Collectively, these are known as the inner transition metals. The first row of the inner transition metals is known as the lanthanides, while the second row is known as the actinides. This is all great, but the truth is that we can get away with a truncated version of the periodic table. It excludes all the transition metals. This periodic table shows only the main group or representative elements. These are elements that follow a much simpler set of rules and patterns than the rest. From here on, I am mostly going to use this version of the periodic table of elements. I admit that even this main group contains a lot of elements. The good news is that a lot of biology requires only 6 of these: hydrogen, carbon, nitrogen, oxygen, phosphorus, and sulfur. The acronym that can be used for these is SHNOPS. These 6 nonmetals account for some 97 to 99% of all elements in the human body. Coincidentally, that is the percentage of people watching this video who have already fallen asleep. Let me take care of the rest of the audience by going over the information provided by each little rectangle on the periodic table. I'm going to pick oxygen as an example. Note that different periodic tables might present this information slightly differently, but the general layout will be similar. In the middle, we have the chemical symbol, and often beneath it, we have the name of the element. Somewhere at the top, there will be the atomic number of the element. This gives the number of protons within the nucleus of the atom. The number of protons is responsible for the identity of the atom. For example, only oxygen has a nucleus with 8 protons. Beneath the chemical symbol, we can find the average atomic mass. Some periodic tables will also give us the information on possible oxidation states. The oxidation state numbers are easily identified as they come with either a plus or a minus sign. The oxidation states are related to an atom's ability to accept or donate electrons. Some periodic tables will also provide us with the information about the electron configuration of the atom. At this stage, you're all thinking that this is more fun than a lard-covered pogo stick, and that you cannot wait to find out more. But let's end this video on a bouncy high. That is all for now, and I will see you on the flip side.